Hello, my name is Chuang Gan. I'm a PhD student from Chuang University. Today is my great honor to be here to present my work with understanding from text to language. And currently, we are in an era of big multimedia data. In a single minute, there are about 300 videos will be uploaded to YouTube. Then, a natural question will arise: how can we organize this large amount of consumer videos? Okay. Let's first take a look how YouTube achieves this goal. YouTube conducts video search based on the keyword match between user queries and the video metadata, such as title, description, or comments. Yes, this is a very effective and efficient way to conduct video search, but there also exists some problem for the video metadata. First of all, video metadata could be lost or irrelevant, since when a user upload the video to the website, we cannot expect that the user can give the video a perfect title that exactly matches the user's searching behaviors. Secondly, we also observe that there are a lot of videos that don't have the video metadata at all. So both of these cases, video search will be faced, and there will be a pressing need to conduct content-based video analysis. And my research focus is on understanding human actions and high-level events from the web and content videos. Particularly, in this talk, I will first introduce my effort to design effective network architecture to learn robust feature representation. My paper published on CPR 2015 is one of the pioneering work that deep neural network achieved success on the large-scale video classification. And we also ranked first in the track with multimedia event detection and also this year ActivityNet challenges. We also provide single best model on the YouTube 80 million challenges. Even though supervised deep learning can improve, can learn robust video representation and make video recognition to achieve reasonable good performance, but we cannot expect this kind of method can scale up the video recognition. So in the second part, I will introduce our work that learning video recognition model from weak supervision. First, I will show how web cloud images and the video can be jointly utilized to learn the video recognition model. Secondly, I will also introduce our method to learning new video concepts through zero-shot learning. At the end of my talk, I will introduce our recent effort that is connecting video understanding to language through visual captioning and visual question segmentation. Okay, let's start from the first part. Currently, there are three challenges for the video recognition. The first part is that there is a large intra-class variation, and also the video data itself is very complex. So this makes video recognition become a super challenging research problem. Secondly, we also observe there are large, it's very time-consuming and expensive to notice the video. This is also the reason why current video recognition data sets are much smaller than the image data. Thirdly, we also found that the concept range of the video concept is much larger than the image net, since that the video concept is always a combination of object, scene, and actions. So the combination is very complex, make video concept vocabulary super large. To address the first problem, we propose that learning video representation using deep neural network. The problem we want to solve is that, first, you give them a video for testing, we not only want to give them a video level label, such as this video is a tapping back trick, and we also want to localize the spatial-temporal key evidence. For example, it's a search snippet containing the back jump, and also it's a back view instead of a background window, make us convinced this is a tapping back trick. To address these challenges, we propose a deep event network that is end-to-end trainable. And also, this network is inspired by the RCN-based framework that will first using the image net data to do pre-training. And then we're using video data to do the fine-tuning. However, different from the existing two-stream of framework that they treat video classification as the image classification. What I mean is that he feeds the keyframe of the video as input and bypass the feed-forward network And finally, they aggregate the softmax classification score over all the keyframes to get the video level classification score. And we argue that video data has another temporal dimension, so we should cleverly leverage the temporal information contained in the video for the video recognition. To best leverage the temporal information, here we propose two technical contributions. The first one is that we propose to change from the single image input as a multiple keyframe, which and you can also call it as a video segment. And secondly, we also introduce a cross-frame mapping layer to insert between the last fully connected layer and the software classifier to enable it to end-to-end learnable. Since that the cross-frame mapping is used to aggregate the feature annotation from multiple keyframes to a single vector and then make it to end-to-end trainable. When equipped with these two technical contributions, our deep event network achieved the best results when we published this paper on the track-with multimedia event detection dataset. I want to mention that prior to this work, the improved data trajectory feature vector dominated video recognition for many years. And this is one of the pioneer work that deep neural network achieved better results than the shallow representation on the web uncontrolled video classification task. And since this is very early work on the video recognition using deep neural network, and we also want to understand what deep neural network actually learn, and we do some visualization here, and we visualize the high response saliency map using some backpropagation method, and we're generating a spatial-temporal saliency map. And here we definitely found that deep event network has learned something very useful for video recognition. For example, you can see the first example, the tapping back trick. It automatically localizes the man read back. And also for the dog show, you can find the region with dog has strong response. Another very interesting observation is about the fourth law about playing fetch. Actually, when I observe this video event, I don't know is dog or person more important for the playing fetch event. And also, I apply an off-shell saliency detection method, and it tells me that the person is more important. But when I apply the deep event network and using some backpropagation to visualize the strong response region, we found that the dog is more important to find the playing fetch event. This is somehow indicated that sometimes machine and human may not correlate well for to make the decision of which class it is. And even though this paper published 2 years ago, it already received some attention for the network architectural design for video classification. I want to mention 2 work. And the first work is the temporal segment network. It's a winner of last year's ActivityNet. And in their report, they have clearly indicated that they borrow our first technical contribution, that they change from the single image input as a temporal segment. And what they do one step further is that they also using this method to the optical flow domain. And the second one I want to mention is the winner of Tumor's challenge in 2015. Actually, they have the same idea of our second technical contribution, is that instead of directly fuse the softmax classification score, they also propose that to introduce a feature encoding, and instead of our cross-frame map pooling, they're using more advanced VLAD encoding. And a variant of this worker also wins the YouTube 80 million challenge this year. And also our work received some attention on the video localization and also about the network interoperability. And I think you are here, and as introduced that we are the winner of this year ActivityNet challenging, and I think many of you are very interested in what the technique we are utilized to win this challenging. And I can introduce some of them, even though they are not published. And the first thing I want to introduce is about a very deep LSTM framework. As you know, that the traditional experience that when we're doing video classification using LSTM for temporal modeling, we also observe that deeper LSTM will entail the performance drop. And the reason may lie in 2 perspectives. The first one is that we always do experience on a small video recognition dataset, such as UCL1, HMB. I mean that we do not need such complex model to understanding the video structure. And the second thing why the performance is not good is that maybe we not clever to design the deep LLM. And the emergence of the large-scale YouTube and ITPNet data that can make us to revisit the conclusion. And here we first naive encrypt the depth of the LLM, and we apply it to the YouTube 8 million and ITPNet data. We find that the performance still not improved. And then we find that when we add, named the fast-forward connection between two recurring units, and we find that the optimization will be much easier and also entail better convergence and also better classification accuracy. And the second thing I want to introduce with you is about shifting attention network. And actually, this network is borrowed from the idea from the success on the Google Brain. They report a very nice result that purely using attention on the machine translation. And here we think the video temporal modeling is, is very similar to the machine translation if you treat each frame as a word embedding. So we also trying that we do not using any LLM or any recurring unit. We only using some attention. How is the result? And very surprising that we only using the attention method, we can achieve very good result. And I think it's it's 1 point better than that using LLM or RN. And also different from the Google Brain paper, we also propose a learnable parameter that enable us to learn diverse attention. And in this shifting attention network, we're using about 64 attention layers to learn diverse region to attend for the video classification. And the third thing I want to mention actually is about temporal exception network. Is that we're using temporal convolutional to replace the LLM or RN unit. Also, this work is inspired by the success of machine translation from Facebook. They propose that using convolutional layer can do the can do the machine translation and also achieve really good results. And here we also using the same idea that we using the convolution layer to do the temporal convolution to leverage the temporal information contained in the video frame, and it also achieve quite good result. And the last thing I want to mention is that we also revisit the traditional backpropagation method when we training CNN for the video task. And the key idea is that that original approach when we train two-stream or temporal segment network, people always treat all the video frames or video segments equally during the backpropagation. And we argue this is not optimal because when we do the classification, we have an intuition that we only need to focus a small part of the video, and then we can do a very good classification. The reason maybe some background frame may confuse us and also make the computation cost very high. So the key idea is that we only backpropagate the very discriminant, and also we have a care divergence loss that to that we only backpropagate some discriminant and also diverse video segment use during the backpropagation, and we found that it will convert better and also achieve better results. Okay, even though the surprise, okay, sure. Yeah, it's very, so the criteria is that because we have a feed-forward network, and we will have the classification scale of, the likelihood of each video segment. So we, based on this, we choose the highest response video segment, and we're only using this video segment to the backpropagation. And to enable some diversity, we also, when we choose the video segment, we also consider some visual and similar segments, and to choose both discriminative and diverse video segment due to the backpropagation.
So this means that at the forward time, instead of passing the entire video, you pass multiple segments.
Yes, yes.
And then it's going to start the backpropagation.
Yes. So we put all the video segment during the feed forward, but we only backpro some of the video segment. And okay, let's come to the second part. And okay.
Question. So how much audio helps for classification?
Okay, I think I should take a table because it's unpublished, but I can tell you it's I mean as a purely I mean it's very black comparison is about I think it's on the ActiveNet we observe about for the RGB. I mean we using both RGB and flow. For the RGB there are about 0.6 improvement, but for optic flow there are about 1.2 improvement on the ActiveNet kinetic challenging data side. Okay, let's go to the second part. That I mean that even though supervised video recognition can achieve reasonable good performance, but as you know, the video data is very time-consuming to annotate. So we should figure out how can we learn video recognition model from weak supervision. And the intuition here is that we first find that the web images and the video, when we crawl from, I mean that when I put a query on the Google image search engine on YouTube, we find that the web return image and the video are always very relevant to the query. Then a question will arise, can we using the web return images and the video to replace the human annotated example to train the deep neural network for video recognition? Even though this is a very fancy idea and also seems very useful, but we find that both the web video and the image contain certain nodes and make the problem super challenging. For the web video, it has the problem of the unfocused problem, and also, I mean, also we can call it as eye trim, is that for a long video, there's only a small part of the video containing the desired event or action. For example, you can see the mopping flow. Only the middle part of the video is about mopping flow. All the other parts is not relevant to the mopping flow. And for the web images, it contains some problem of the semantic drift and the domain gap. For semantic drift, I mean that for them you can see the juggling ball with the juggling ball query. The web return images are all about the ball, not about the juggling ball. So we cannot expect such of domain gap images can train a really good classifier for the video classification. And we also find that there are also some domain gaps between web image and video data. You can see the third example. The return web images are exactly the baby crow, but they are all in the white background. It's very different from the video cluster background. So we also cannot expect such data can work well on the video data. And it seems that both of the nodes from web images and the video data cannot be removed that only based on their own domain. Since that, as you know, that's more like super learning. We do not have any supervision here. But we found a very interesting observation here is that the relevant web images and the video frames, I mean, the relevant part are always very visually similar, but their irrelevant part has their own distinction. Or in other words, that the noise part of web images and the video frame are differ very much. We can find the example, for example, for the noise from the web images, the noise maybe are more about the logo, some cartoon images. It will not very likely to occur on the video frames. And also for the video frames, the noise from the video frame, maybe some background, such as the audience or something others, is also not very likely to occur in the web images. So the problem turns to that if we can select the visual similar part from web images and the video, and I mean keep those in common, then both of the nodes and the nodes from web images and the web image can be joined, removed. And based on this intuition, we propose a lead exceeding network. Let's go to it. And the first part is that we first take the frame of video as input to train a leading network. And this network do not have the ability to distinguish the relevant video frame or irrelevant part. But it has one other benefit that it can be used to select the relevant web images. As I have indicated that the visual similar part of the video frame and the video and the web image will rank higher than the noise part. And then we can using a threshold to remove out some logo or cartoon images. And the web images has the benefit that because it always contains the highlight, and we can then add the selected web images into training to train an exceeding network. Since that the web image contains the highlight, so the exceeding network will have the ability to distinguish the web relevant images, the the relevant video frame from web images. So we can we can back using this existing network to trim the video. Then the noise, during this iteration, both of the noise of web images and the video frame will be removed. Then finally, we can train a temporal model and to model the temporal dynamic and for the video recognition.
A couple of questions. So one is this, you're removing frames within the video and you train a temporal model. Aren't you worried that you're going to actually change the temporal sequence of things?
Okay, very nice question. And here, the first thing that our framework actually is you can consider as a two-stream network. And the first stream that we only take the RGB images in, the RGB frame in, and we add the web image in to tree seating. So this is more like the spatial stream. And then the second one is, as you mentioned, is the temporal stream, is that we only select the relevant video segment. And then we put the video, we put the video segment into LTM to train a temporal model. So this is the story.
And what is the role of the classifier in the lead network?
In the lead,
what are the labels?
Because we're using web cloud video, we take the query, for example, particle down, and then we retrieve maybe top 25 videos, and we take all the video frame as.
And do you do that multi-class, or are you doing for?
We do multiple class. For example, for the UCI1, there are about 101 classes. So we call out each classes and train multi-class. The top of them is softmax clarifier to clarify each video. Yeah. Okay. Okay. Let's first show some ability study result on the UCY1 action recognition data set. And this data set has there are about 10,000 video. And that for each video, it maybe belong to one of the 101 classes. Here, we first show the result that we only training the network using the web images and the video. It will achieve around 60% result. And when we join using the lead EC network, we will improve the result over 10%. And here is another combination approach of web image and video. For example, we first train two models, and then we rely on late fusion. You late combine the classifier of two models. You can achieve 6%, 67.8. This indicates that web image and web video are complementary resource for training the video recognition model. But that when we clever do it, we also achieve, that using a lead EC way, we can achieve better result. And also we compare with the result of the mixing is that we mix the training web image and the video. We blend do it, and you can see the performance is also not well as our lead EC network. And we also test on more general track width, multimedia event detection, compared with other widely supervised approach, and we achieve significant better result. But I want to mention that our success may benefit from two parts. The first part is that we're using the deep neural network, and other approach do not leverage this one. And second part is that our leading exceeding method that to join using the web image and video is another benefit for our true better result. And even though that widely supervised approach can make video recognition somehow can scale up, we can train many video concepts as our desire, but we still cannot expect that we can pre-train all the video concepts beforehand. So in the third part, I will introduce our method to learning new video concept vocabulary using zero-shot learning. First, I want to give a brief introduction about the problem setting. Is that first you give a textual query, and maybe you have 200,000 videos, and we want to return a ranking list that to indicate each video how it will be relevant to the text query. So it's more like a text-based video retrieval approach. The text query-based video retrieval research problem. And the traditional problem is that, the traditional solution is that they first embed the video and textual query in a common feature space. And then they may rely on a dot product to do the retrieval. And we argue this is a very effective and efficient way, and also a traditional retrieval-based framework for the video recognition. but we argue that it cannot leverage the interclass relationship contained in the video concept vocabularies. Let's give an intuition list, intuition example about what we, how we solve this problem. For example, if I want to recognize the new concept vocabulary of soccer penalty, even though we do not have this kind of video data, but we may have some relevant concepts such as field hockey penalty, soccer juggle, or others. And the intuition is that if a video very relevant to both field hockey penalty and soccer juggle, it will be very likely to be the soccer penalty. So in other words, if a video have both higher detection score of field hockey penalty and also soccer juggle, it will be very likely to be the soccer penalty. So the problem turned to given a new video concept vocabulary, how can we identify the relevant concept from a large predefined concept pool? And we using a data-driven word-to-vec-based approach is that we compute the semantic relevance score between a novel concept vocabulary and all the predefined concept. Okay, let's give a concrete example. For example, there's a new concept vocabulary named front chrome swimming. This is a novel video concept, and we want to learn classifier to distinguish these classes. And first, we compute the semantic relevance score between front cloud with all the predefined concept pool, and we will returning a ranking list of all the video concepts. For example, the breaststroke swimming have the higher semantic score, and the baby curl ranks third, and also maybe some other concept ranks lower. And then we can train a ranking function in this part that we can, based on the visual feature and based on the visual example and relevance score, to train a ranking function that makes a classifier to clarify some video that's most similar to breaststroke and the baby curl higher, and then it will be very likely to be the front chrome swimming. And with this very simple and intuitive approach, and we achieved the best result on TriVid multimedia event detection challenge 2015. And the only winning secret is that we leveraging the interclass relationships contained in the different concept vocabulary, and other team may most rely on the the black box embedding-based approach. Okay, let's come to some more interesting part. Is about vision and language. And the first thing I want to introduce my work about attractive visual captioning. Okay, the research problem. Okay, the research problem is that we first found that the currently state-of-art visual captioning system always give a factual description or global summary of the image content or video content. Such as these images, the traditional caption maybe people use a smartphone, a pretty girl sit on the beach. It's just a boring summary of the image content. And maybe we can see it in a more attractive way. For example, smartphone, not make me smarter, or something pretty girl, you don't love me. Then we argue that a very that we can generate the caption in a more attractive way, and it will have many benefits. And we also found that the style, such as romantic humor, is a very effective way to make visual caption very attractive. And the benefit of the attractive, the attractive caption view is that we can first find these images. It can be make images more popular. We argue that for these images, they become popular not only because not only due to their image content, also rely on them. They have very attractive visual captioning. And another very real application is that when I upload images to the website, such as YouTube, such as Facebook, Flickr, it will always take me a long time to figure out a very attractive caption that can make more people like my picture. So I'm thinking that can we use a machine learning data-driven based approach to automatically generating attractive caption? And to achieve this goal, we propose a StyleNet framework, and we also and the building block of the StyleNet is the factor LTM. And here is the traditional here is the traditional LTM. It has the input gate, forgettable for get gate and output gate and something other. And the factor LTM, the tutorial is very easy. Is that we reparameter the weight vector of the traditional LTM, the W into 3 parts, U as V. First, I want to tell you that U as V doesn't mean the SVD. It's just the learnable parameter U, S, and V. And our intuition here is that we want a subvector of W, U and V, to control the content for the caption generation, and using S for the style, for the style control. And based on this intuition, so we're using the matrix factorization to model this. And our training framework of StyleNet is okay. First, let me introduce the input. The input of the StyleNet is that first we have the paired images and the factual caption. This is the standard style caption. It's paired with images. And second, we only have the monolingual romantic sentence and humor sentence without the paired images. Since, as you know, that it's very time-consuming and expensive to gather the paired paired images and the style caption. So here we want to leveraging the off-shelf language corpus to distill the style from the language corpus and incorporate this style vector into the caption generation.
But these sentences do not correspond to the same.
No, not correspond. It's only the off-shelf monolingual sentence. So this is more like unsupervised learning the style. And to achieve this goal is that we leveraging the factor LTM, and also we design a multitask learning framework. The first task is that based on the image content, here we generating the standard style LTM. Using the factor LTM is that as the input is the encoder decoder framework. The encoder output is the image feature vector, and then we're using them to initialize the factor LTM and do the decoder to generate the caption. And in the second task is that we take the romantic sentence as input that we using the factor LTM. It's more like auto-encoder and using LTM, using factor LTM as a language model. Is that you given the first word, you predict the second word. And also the third task is based on the humor sentence, also using factor LTM as a language model. During the
you learn U, S, and V, or you're fixing U and V?
Yeah, this is I will introduce next step. During training, we share the parameter of U and V among different tasks. And S is a style specified. For example, if when I'm training the factual caption, we're using we're using SF. When we're training the romantic sentence, we're using SR. And also if we're training the humor sentence, we're using SH. But U and V are shared among different tasks. And so since U and V are shared, means that it will enforce that U and V to control the whole content, to capture the general pattern of the language, and S to be style specified. So during the caption generation, sorry.
But when you're doing factual caption, U and V are going to be also controlled by the input to the hidden layer, like the CNN output.
Yeah.
But here there is no.
Yeah.
The tasks are quite different, right?
Yeah, because when we're using the factor LTM and the image feature only as the initial, the first, or you can say zero state initialization, and in here that we initialize them as a random variable, and without any image input, we randomly initial vector and then using the other part as to capture the language pattern in the language corpus. And during the caption generation, during the testing phase, we take the input of images. We also try the feature vector, and then we only we can using the style vector X to control which style we want to generate. For example, if I want to generate the factual style caption, we can use SF. And if I want to generating the romantic sentence, we can use SR. And also if we want to generate humor, we can use SH. So here S is more like a style vector to control which style of caption we want to generate. And here I want to show some example. For example, this is it's the images, and this is caption generating by the the traditional caption bot. For example, it says a dog laying in the grass is very boring. And our romantic caption is that a dog ran through the grass to meet his lover. And also the humor part will be a dog running through the grass in search of the missing bones. Okay, let's find another example for them. Okay.
So this USV has some constraint?
It's no, it's just a learner parameter. It will share. It's just a learner parameter. Yeah.
But then what's the difference between you just learning the USV or just WF and WH and WR?
Sorry, can you say again? You mean that you?
So if there's no constraint on USV, then
Because you. So you mean constraint means what? Sorry.
S should be diagonal.
No, there's no constraint. Yeah.
So then what's the difference between learning the WH and WR and WF?
Oh, you mean separate? You mean that you?
What's the benefit of factorization?
Exactly.
Yeah. That's a very nice question. And I mean that there's many different methods because when we submit the paper to CPR and also when I presented the paper, many people also ask me why. The first question maybe why do you need to decompose the factor to 3 parts? Maybe you can also decompose to two parts. And the reason of this part is that because I mean that if you have two another space, it will have larger certain space and making the training more adaptable. And the second question is that why do we need to do the factorize? How about you train 3 separate LTM and to achieve the performance to achieve goal? And the first I want to answer is that I mean that you can also only using 1 parameter and without any domain adaptation. You can only train 3 parameter. And actually in this paper we have a comparison about that without factorize. We can get in blue skull we can have 1.2 improvement if we using the factor approach. And we also do some human evaluation. And it also seems that the factor RTM, because you separating the content and also the style during the training. For the caption generation during the evaluation, during the human evaluation, is also voting better. And we speculate the reason is that actually this work, the style and content disentangle actually is a well-studied research problem in the video domain. Many people, that they will using a factor method to maybe there are people running and he want to factorize the background and the moving point. They're also using the factor method. Actually, we borrow the idea here and using on the language control part, and we find it works really well.
But I thought U and V are shared across these stuff.
Yeah.
Right?
Yes.
So that's the benefit.
Yeah.
Because you cannot train a humorous model because you don't have paired data.
Yeah, we don't have. That's another. Yeah. Yeah. So you can using U and V to share. Yeah. Okay. This is another very interesting observation. For example, the camera will generate a man on a rocky cliff and next to a stone ball. It's a very boring caption, and we can say that a man is used coping to conquer the high, or some humor caption that a man is climbing out like a lizard. And also we show that this kind of method and data can also transfer well to the video domain. For example, this standard style caption is that, for example, a man is playing the guitar, and the romantic way we will say, a man playing guitar, dream of being a rocking star. And also the humor one will be a man is playing guitar, but runs away. So that when we leveraging the StyleNet, we can generate very attractive caption. And also this work is on the way to transfer to the actually, this paper is published during my internship last year on the Microsoft, is on the way to transfer to product.
So the romantic and the humorous matrices, the WR, WA, or whatever, which are S.
Yeah.
So they are trained purely on textual data.
Yes.
So is my understanding right? The way you're being able to generate this romantic sentence is it has learned what romantic phrases go with what concepts.
Exactly.
Only.
Yes, exactly. It's just, I think, so this is a very nice question. And we also figure out that, the factor actually is more like the, you can also to to learn that when we talk about some concept, how this, the romantic, how can we say it in a romantic sentence? So you'll see here more about that when we condition on a concept, they will say something others that makes them a little bit romantic or humorous.
Well, but I think the main question is, I can do the same thing by ignoring the video and just use a romantic language model.
Yeah, that's a very nice question, but I miss that because you can see that we first condition an image to generating some content, and then we can figure out which kind of language we should, which kind of romantic part we can say it.
But do you ever observe you're actually generating a new
yes.
style?
Yeah, this is a very nice question, and we also want to figure out if the StyleNet is just a copy some sentence from humor language corpus, and we found that it's means that there are some language pattern. For example, it's just a copy from the current, but we found some new combination of the content of the the humorous and romantic part. I mean that for the the word in the color, it's always some repeated pattern. But for but the combination.
Example, if you go back, it's climbing like a lizard.
Yeah, it's always saying this way. I mean that.
So
yeah.
In your training,
It's
actually like a lizard.
Exactly.
Climb.
Yes, it's always saying that climbing out like it's something. I mean that it sometimes remembers the data, but but it's also conditioning on the image content, but saying it in a romantic way.
Have you tried taking your, let's say you take your humorous LSTM, right? And then you feed in first 5 words like man is climbing.
Yeah, and then you repair.
From it. Like, does it choose a lot of diverse things, or is it basically learned a one-to-one mapping between climbing and lizard? Or?
Yeah, this is another very nice question, and we also, when I submitted the paper, I also found that there's the diversity of captioning is not good. I mean that it always repeats some pattern, and so we have another work, a follow-up work that we introduce some DPP in. That to incorporate some diversity constraint and into the caption generation to avoid repeating pattern. But during I submitted this paper, it also has some problem of the repeating pattern. Another question is that that we also figure out, because when I submitted the paper, they also cannot do some mixed style. For example, 0.5 humor, 0.5 romantic. And in this one, we cannot do it. But in another journal submission, we also propose using that we can controlling the content. The extent of how much style we want to incorporate in the caption generation using some other using a more advanced metric factorization approach.
Have you visualized the location or the regions of your image or video that is firing on these sentences?
Currently we are not, but it's very interesting research direction to study. Yeah. Okay, and here I also want to introduce another. I think is what the next step of the visual captioning. I'm arguing that the next step of visual captioning we should leveraging some outside knowledge base to do more deep understanding of the image content. Okay, let's give you a concrete example of what I'm doing right now. For example, for these images, the traditional caption may be generating that a herd of elephants standing next to a man. And with more, the celebrity entity recognition, we can understand this man is Obama. So we can say a herd of elephants standing next to Obama. And when we combine with the knowledge base, we can do some reasoning here. For example, Obama is the president of the Democratic Party. And the competitor of the Democratic Party is Republican Party. And the mosaic of Republican Party is elephant. So we can generate a very deep understanding of the image content is that Obama is chased by his Republican competitor. So this is more like that we can leveraging the off-shell knowledge base that how the visual concept related to deep understanding the image content. And also we argue that for the original caption, it's more like a 10 years child that he can understanding what's image content. But with more reasoning part, that the intelligent visual captioning system may have an adult intelligence that it can do some reasoning to understanding what appeared or hide in these images. Okay, and the last of work I want to introduce our most recent work about visual question segmentation. And the intuition of okay, first I want to introduce what I'm doing is that we build a connection between visual question answering part and also visual segment. I think you're all very familiar with the visual, the VQA, visual question answering, is that you give a question about the images, and then you will give a text answer to answer the question about the images. We argue that the traditional visual question answering task, even though it argues it will be used to, to capture the machine intelligence, to join understanding the visual content and also the language part. But we argue there is some shortcut. For example, for this image that he asked, is he wearing a tie? If you only answer yes or no, actually there will have about 50% you get the right answer. But you don't know if you exactly localize that where is the tie is. And also another example is that if you ask question, if the street empty, also you ask yes or no, you will also have about 50% to get right. But you cannot, if maybe he don't understand that it's because there are two cars here, so make you answer no, this street is not empty. And so our argument is that instead of only giving the text answer about the question about images, we should also localize the region. That's why we make the decision. And it will somehow avoid the shortcut of the visual question answering task. So here we build for each question on the VQA task, we will annotate the visual region that can answer these questions. So we name this dataset as the visual question segmentation dataset. And we also show that with this new label dataset, we can enable two fundamental tasks. The first task is about the question focus semantic segmentation. The problem is that you give a question and you give an image input. He will first learn to where to focus. Where's the visual answer to answer this question. So this will best leverage that you should understanding the image content instead of only give a text answer. Right? And we also show the second task that with our annotated data, we can also enable the supervised attention for the traditional visual question answering. That we using the annotated data during training that we can learn to attend which reason and to better understand the image content. And we show it further, I will show appearing results that when we use it as data, we can get many benefits to improve the traditional visual question answering task. First, I want to show you results for the question focus semantic segmentation. And here we propose two methods. The first method is the DevNet is that it's more like the decode-based framework. You take the question and image in and using encoder, decoder to have the output segmentation mask. And we also using aggregation-based approach. Is the idea that maybe you have we first leveraging a segmentation proposal network that he gave you some candidate of the answer, and then we learning aggregation that how can we combine the segmentation proposal to generating the result. And here I want to show the result about the aggregation-based approach is slightly better by decode, but it's significantly worse than the traditional visual segmentation task. This indicates that the pixel level understanding from natural language expression is a super challenging task, and we need more effort on it. And here I'm show that the result, actually we only annotate about 10% of the original VQA dataset. And we using this data, it's more like the previous learning that we using this data to learning a supervised attention model. And we find that we simply add the attention feature, we will get 1.5 improvement on the VQA dataset. This, and also we ensemble the model. It's the most naive approach, but it can achieve the best result. So this somehow indicates that if we want a machine to think, to reasoning, to understanding the images, we should first teach them where to attend to understanding the region among the images, then we can achieve better results. Okay, finally, I want to conclude my work. And first of all, my work is one of the pioneering work that successfully applied deep learning for the video recognition. And also, we pave a new research direction to utilize the web unlabeled, the web cloud images and video to train deep neural network for the video recognition. And also, we propose a new method by connecting knowledge base to leveraging the inter-class relationship for the zero-shot video retrieval. And also, we can call it as an open vocabulary video retrieval. And fourthly, we take a step further to generating some attractive caption. And finally, we also collect a new visual question segmentation dataset to facilitate better understanding the vision and language part. And in the future, I'm very interested for the 5 research direction. The first one is that, as you know, that the original video recognition deep network are all the human design. And here, I'm very interested that how machine can replace the human effort to replace the network architecture design. So I'm very interested to using meta learning or learning to learn combined with reinforcement learning to let the machine automatically design the neural network architecture. And second part, I'm very interested to connect video understanding with knowledge base, such as the Obama example that we can leverage the off-shell language corpus and knowledge base to do more deep understanding about the video content. And thirdly, I'm also very interested to understanding human and object interaction. It's more like connect video understanding to robotic. For example, that people by watch video, they can learn many new abilities. For example, if I want to repair an iPhone, and maybe we can watch a set of video, I will know how can we repair the iPhone. And I want the machine to have the same ability that watch a set of video, and they can simulate some action. And the first part, I'm also very interested about the generative model for video analysis. For example, how can we predict the future? How can we speed up the video? And how can we, for example, how can we convert the 2D video to 3D video? So how can we do it? And as any part, as I'm always treating video as a knowledge base, that how can we leveraging the unlabeled video to do some unsupervised feature visual knowledge discover? For example, how can we leveraging the unlabeled video to do the novel view synthesis, to learning object classes, also to understanding causal relationships. So this is what next I'm very interested to do. Okay, that's the end of my talk, and I would like to take any question about my talk. Okay.